Hello, followers of my YouTube channel. Welcome to today's tutorial on GIS Hydrological application. It is about watershed delineation and flow computation. Okay, so to start with, let us first what mean watershed delineation. All right. So watershed delineation is actually the process of identifying the drainage area of a point or set of points. Yeah. So for many years in the past years, water engineers as well as different professionals have using EMA paper for mapping watershed. Okay, just like this. On the right, and this EMA paper has almost this much scale, 1 to 50,000 scales, and it is a UTM, Universal Transfer Mercator. Therefore, as you know that the water flows in the directions of the terrain, steepest downhill slope. Yeah, if you see this map, the directions of the water, as it indicates, is to the downhill slope. Okay, therefore, streamlines are orthogonal to the elevation control lines. They are orthogonal to the control lines. All right. If you observe this map, yeah, this section is this area is, as you see, a river, or that is actually the looks a gorge area. Okay, so the flow of water is towards this. Okay, so these streamlines do not flow towards the drainage divide and do not intersect them. As you know that the drainage divides are found along the highest point of the terrain. For instance, this red color is the drainage divide of this watershed, and this point is the outlet of the watershed, as it marked based on EMA paper. Okay, so nowadays this EMA paper is not applicable, and the DM, or the digital elevation model, is used in order to delineate a watershed. So these DMs store the same type of information or control lines do, but with a different data structure. Yeah, from the previous one, from the EMA paper, should have to see the control lines, but we may get a different data structure in DMs. In addition that, the watershed delineation can be based on the DM rather than the control lines. So now for instance, for a taping context, we have 30 and 90 meter DM, which is developed by this SR team. Yeah. In addition to that, we have also an access on 12.5 meter resolution DM data from Alaska Satellite Facility. Okay, so you can use those DMs, okay, that have resolutions of 30, 90, as well as 12.5. Still we have 5 meter resolution DM. Yeah, so we can see, for instance, we can visualize the difference between this 30 meter as well as 90 meter resolution DM. Yeah, so when this resolution is increasing, yeah, it covers a small area, but we can observe in a larger way, yeah, in a clear way. But when we see the in the case of 90 meter resolution, it covers a larger area, but its clarity may be somehow not as much as that of 30 meter resolution day, and vice versa. Okay, so in order to get the DIM from different internets, yeah, for instance, for the case of 90 and 30 meter resolution, you can obtain from the topographic machine digital elevation model. That means it's RTM, shutter radar, topographic machine. From this link, you can get this 90-meter resolution. In addition, from Earth Explorer, we can get 30 meters. And from the Alaska Satellite Facility, you can access 12.5 meter resolution day. Okay, so those are the websites that you can access the elevation models. Okay, for the case of 30 as well as 90-meter dam. You can have, you should have to find those dams. So let us proceed with the details on the watershed delineation. So in order to delineate a watershed, the first thing that you should have to do is you should have to load the DM data into your Arc map or Arc GIS. And after that, you should have to do the flow sync, mean field syncs. Yeah, we will see why we are doing these field syncs. And should have to compute the flow direction and flow accumulation. And should have to do or define the pour point. Okay, should have to define the pour point. And finally, we can generate a watershed. So we can get the drainage area of a watershed using those steps. Okay, should load, field sync, compute flow direction and accumulation, define the pour point, and finally the generate a watershed. Okay, so let us see what means the flow field sync. Okay, so this DM creation results in artificial sinks in the landscape. Okay, so we may get artificial sinks under the DM. Yeah. So in order to remove those artificial sinks, should do this field sync. Okay, you should do this field sinks. In a sink is a set of one or more cells which has no downstream cells around it. Okay, so those sinks does not have downstream cells, and actually there is no downstream flow of water after this flow sinks. Okay, so should have to remove it before you should proceed to another step. So this field sync is the first step for processing a dam for the surface water system. Okay, so unless these sinks are filled, they will isolate portions of the watershed. So that is why we are working on the field sync before we proceed to flow directions. Okay, so for instance, if you see here the input map for the field sync, around these sections of the map, the value is lower. That means the value is 2. Yeah. So if the water under this section may sink at this point, it does not drain from the watershed. So you should have to fill it with a minimum value around this one. Okay, so you should have to substitute or should have to fill the sink using the minimum value around those points. So in such a way, you can or we can fill the isolated parts of the dam. Okay, and you can also see the hydraulical slope here. Okay, should have to know from where to where the water is flowing. Okay, the direction of the steepest descent should be very important in order to know or delineate a watershed. Is it from this one to this one, or from this to this, or it may have 3 options? But in order to know that, should have to determine the slope. For the instance, for this case, the slope between this and this is calculated by using this one. Okay, actually this 30 is DM resolution, okay? A DM's resolution of 30 metro. So you could have to know in such a way, okay? So the water is flowing to this one because the slope is this. This one is the steepest one. So the water is flowing in such a way. Therefore, you can have about hydrological slope is very important. And the other is flow direction. You should have to know about flow direction. Yeah. So in order to know the flow directions from where to where the water is flowing, you should have to know about 8 direction 4-point algorithm. That is the D8 assigns us the flow direction code to each cell based on the steepest downhill slope as defined by the DM. So this D8 algorithm is very important, all right, in order to know the from where to where the water is flowing. So the flow direction code indicates the cell out of the 8 neighboring cells toward which the water is flowing, and the flow direction cannot be defined for cells within steering depressions. Actually, you can observe this. Okay, it has 8 the 8 algorithms. For instance, 1, 2, 3, 4, 5, 6, 7, 8. Yeah. If the direction looks like this one, you should have to provide 1. Okay, the direction is 1. And if the flow direction is in such a way, you should have to write 2 on the side. And if its direction is like this one, you should have to write 4. And if it is upward like this, that is 64. And if its direction is just like this one, you should have to give us 128. So 1 plus 1 is 2, 2 plus 2 is 4, 4 plus 4, 8, 8 plus 8, 16, plus 16, that means just like that. We are obtaining these values in such a way, okay? Therefore, in order to know the flow directions, this 8 direction 4-point algorithm is important. So, for instance, let me see this one. Okay, for this case, this is actually the assumes that the elevation or the DM data, and we have this value. The elevation at this cell is 78, and at this point 74, at this point 72, and at this point 67. Yeah. So if you see the values here, the elevations, this one is a loss larger than that of 72 and 74. So the flow direction from this should be to this one. So if we come up with this, yeah, if you come up with this, the flow direction is just like this one. So you should have to provide 2 for the first cell, that is for this one, 2. Yeah. And for instance, let me come with here 69. This 69 may be flow to this one, this one, this one, this one, or this one. So for the surrounding cells or the elevations, the smaller elevation is this one. So the flow direction is just like this. Yeah. So in this case, you should have to know that. Come back with the top. Yeah. If the flow direction is just like this, you should have to tell us the flow direction is 1. All right. So it is 1. So those flow direction grids are prepared by using the this D8 algorithm, alright? So you can have an access in such a way. And this may be flow to this one because this cell is smaller than this or this and this one. And this may be flow to this one, yeah? Because this value is smaller than the other one. The slope is high between this one and this one. That's why. And this may flow to this one. Okay, that's why the direction is just like this. So this line, this plot is done or created by determining the slope, or you can have an access to determine the slope between the points. For instance, between this T21. This T21 is the flow from this T1 grid T21 to this one, yeah, because the other is larger than this one. So directly this is go to this one, and the flow the value is 1, yeah. So in such a way, you can create a flow direction grid. Okay, network. This one is a grid. This is a DIM. This is a flow direction grid, and this one is a flow network. Okay, the flow network is not a grid. Actually, it is a network. The direction. So as it indicates, the flow of water from this cell to this cell, the flow from this cell is toward this one, then toward this, and the like. So our outlet is at this point, it tells. Okay, so always you should have to start at this one. Okay, in such a way. And the other is flow accumulation. Okay, the number of cell contributing flows. Yeah, this is actually the when we are talking about this flow accumulation, we are talking on number of cells contributing to flow. Okay, so the flow accumulation is a measure of the drainage area in units of grid cells. If you have this one is a dam actually, and for instance, for the surrounding cells, at the top and at the left, there is no contributing cells toward this. Therefore, you should have to provide 0. And if you proceed with this one, for this cell, this elevation 78 goes to this one. So therefore, you should have one cell that contributes to this one. So you should have to give us 1. Okay, and for instance, for this case, we have gauge 3. Yeah, for this one, that means cell. I mean the elevation or the DM cell value here 74 goes to this one, as well as 69 goes to this one, and also 64 goes to this one. That's why this cell has a contribution of 3 cells, okay, for flow. So when we are working with this flow accumulation, the cell itself is not included. Rather, you should have to incorporate the previous cells, okay? And the function is a flow accumulation. The input is the flow direction. Okay, you should have to provide the flow direction. To make your determination for the flow accumulation grid, you should have to use a flow network. If you use a flow network, it may be easy for you. So you can work on such a way. And when we are working on flow accumulation under GIS, you may get such flow accumulations or lines. Yeah. Therefore, from a flow direction map, a flow accumulation map can be derived. In the cumulative flow for a cell is the number of cells that flows into this particular cell. Okay. And cells with a value 0 have no other cells flowing into them and represent as higher areas. Okay, those areas are higher areas. And cells with a higher accumulation flow counts represent as streams. Okay, high accumulation flow areas are streams, actually that's the rivers. Okay, so in a similar way, you can try this for the flow accumulation. Okay, therefore you should have these stream delineations. You can delineate streams. Okay, so all grid cells draining more than a user-defined threshold value. It's the blue streams are part of the stream network. If you see here, for instance, those are the small rivers that contributes to this the larger one, and we can say that those are the streams. Okay, So you can define the stream or stream delineation is helpful in order to get those such types of rivers. Okay, and as well as stream links are there. Okay, so finally we can have an access on the outlet. Yeah, so we have a dam, we have the stream link. Okay, and finally we can have an outlet here. Yeah, you can may have this one, but in order to contribute all of the these dams, you should have to take your outlet at this point. So in such a way, you can get an outlet. And finally, we may have say types of polygons. Okay, different polygons that contributes to some watersheds, and those are the streams. Okay, the streams. So the drainage area of each watershed outlet is delineated now, and the grids of the stream links and the watershed are vectorized to obtain streamline and watershed polygon datasets. Okay, so this is a way that you can delineate a watershed. So in conclusions, this hydroparameterization, after you have delineating a watershed, you can obtain the catchment area. Okay, you can obtain the catchment area. We can get also the slope. Okay, we can get the slope. In addition, we can get the longest flow paths. Yeah, the longest flow paths. And also we can have an access to know about the slopes of the longest flow paths. So this tutorial is very important in order to know those parameters from watershed, and in order to further do hydrological studies on the delineated watersheds. And I think it is very important for you guys. So it is all about today's tutorial, and have a nice time. If you have any questions regarding to today's tutorial, you can have an access to put your question under the comment section. Have a nice day.